All right, in this video, we'll be learning how to simplify radical expressions. And simplifying is just taking an expression and rewriting it in a less complex way. So let's do some exploration to come up with a general property that we can use. So let's say we had the square root of a product 4 times 9. Well, we could simplify this by simplifying the expression inside or underneath the radical sign. 4 times 9, that's the square root of 36. And since 36 is a perfect square, we know that we can simplify it to it simplifies to a rational number. The square root of 36 is just 6. Now, let's say I were to rewrite this expression. Instead of having the square root of a product, we have the product of square roots. So what do I mean by that? Let me rewrite this as the square root of 4 times the square root of 9. Essentially the product of these two square roots, the two factors of 36. Now let's see if that gets us the same answer. Well, the square root of 4 is just 2. And the square root of 9 is just 3. So this is the same as saying 2 times 3, which is indeed 6. So we can see that if we have the square root of a product, that's equal to the product of those square roots. And so we're going to extrapolate a general property here, a property we're going to call right now the multiplication property of radicals. And it goes something like this. If you have the square root of a product A times B, that is equal to the square root of A times the square root of B. Now you might say, well, you've taken something very simple and made it more complex. What does this have to do with simplifying radicals? It seems like this is taking a simple radical, the square root of A times B, and making it more complex, the square root of A times the square root of B. Fair enough? So let's see how we can apply this to make some radicals a little simpler. Let's say we've got the square root of 12. Well, if we could rewrite 12 as the product of two numbers, let's say the square root of 2 times 6, can we use this property to simplify this product, or the square root of this product? Well, actually, no, we can't. The square root of 2 times 6 is just the square root of 2 times the square root of 6. And the square root of 2 is an irrational number, and the square root of 6 is an irrational number, so this is really not going to work for us. This doesn't help us at all. However, if we were to rewrite the square root of 12 as the product of this, or the square root of 4 times 3, well, now does this property help us to simplify the expression underneath the radical sign? Well, let's see. Here, this is going to be the square root of 4 times the square root of 3. Square root of 4 times the square root of 3. And sure enough, the square root of 4 is a rational number because 4 is a perfect square. The square root of 4 is 2. Now, the square root of 3 is an irrational number. We're not going to be able to simplify this so that it's completely composed of rational numbers. In fact, the value of the radical has not changed, just the way we represent it. So we're going to keep that square root of 3 as square root of 3. But instead of writing square root of 12, we can rewrite the square root of 12 as the product of a rational number times an irrational number. So essentially we've taken the rational part out of this larger number 12. All right, so the square root of 12 is going to be equal to the square root of 2 times the square root of 3. Now, how did we accomplish this? We factored out the radicand, or the number underneath the radical, as the product of a perfect square and a non-perfect square. So what you want to do is you want to factor the radicand as the product of a perfect square, and some other number. So let's see if we can apply this to simplify some other expressions. So let's say we had the square root of 50, square root of 50. We can rewrite that as the product of, or the square root of the product of 25 times 2. And we know that the square root of 25, our perfect square, is just 5. And we know the square root of 2 is an irrational number, so we'll leave that as the square root of 2. And so we've simplified the square root of 50 as 5 times the square root of 2. Let's take another example, the square root of 18. Now feel free to pause the video and try to simplify this yourself using the multiplication property of radicals. All right, so I'm just going to go ahead and solve it. Pause the video before I get to the answer if you want to try it yourself. So I'm going to factor 18 as, well, let's see. I could factor it as the product of 3 times 6. That equals 18. But neither 3 or 6 are perfect squares, so that's not going to help me at all. However, if I factor it as the product of 9 times 2, well, 9 is a perfect square, and I know that the square root of 9 is just 3, and the square root of 2 is an irrational number, so I'm going to leave it as the square root of 2. I can't simplify that any further. So now the square root of 18 equals 3 times the square root of 2. And you can check all of these in your calculator. If you plug in the square root of 50, and then you plug in 5 times the square root of 2, you're going to get the exact same decimal. They literally are equal to the exact same value. It's just this is the simplified version of that. Let's try one more and see if you can do this one totally on your own. The square root of 20. So by now, why don't you pause the video and see if you can at least factor 20 as the product of a perfect square and another number. So what you should have done is you should have found that the square root of 20 is the product of 4 and 5. And we know the square root of 4 is just 2, and the square root of 5 is just the square root of 5. That can't be simplified any further. And that's about it. There's nothing more complex, or there's nothing further to know about simplifying radicals. So now what I'm going to do is I'm going to give you a problem. Should be familiar if you've watched the other videos. A problem involving a right triangle, so a Pythagorean theorem problem. Let's say we have some right triangle, and we're given the legs 4 and the legs 6, and we want to find the length of the hypotenuse. So by now we should know what to do. We're going to use our Pythagorean theorem, a squared plus b squared equals c squared. And a and b represent our legs, so we're going to square the two legs. 4, we're going to square 4 squared, and we're going to add that to 6 squared, and that's going to equal the length of the hypotenuse squared. And 4 squared is 16, 6 squared is 36, and when you add those together, you get 52. All right, and 52 equals the length of the hypotenuse squared. Now what happens when you take the square root of c squared? You get the length of the hypotenuse c. And what happens when you take the square root of 52? Well, the square root of 52 is an irrational number. We know this because 52 is not a perfect square. However, so we could say that the length of the hypotenuse is the square root of 52. Now this in a way is acceptable, but you always want to write your answer in the simplest way possible. So we want to first check, can we simplify the square root of 52? And it turns out that we can. 52 can be factored as the product of 4 times 13. And we know that the square root of 4 is just 2, and the square root of 13 is just the square root of 13, an irrational number. So we could rewrite the square root of 52 as the product of 2 and radical 13. And so although they're both equal to each other, 2 square root 13 is the preferred way of writing this answer. And that would be the precise length of the hypotenuse of this triangle.